Hello and welcome to follow my videos. My name is Matti Ylitalo and today our focus is unsteady conduction, so-called slab cooling problem. Just a second, I'll put the presentation mode on. Slab or bar, whatever you call it, is a piece of material in which these cross-sectional dimensions are small compared to the length of this material. I used 0.25 meters times 0.5 meter cross section, and when I carried out a CFD simulation I used the length of the bar 3 meters. The material of this slab was stainless steel, so this lambda value was 15 watts per meter Kelvin, and I used initial temperature 90 degrees C, and I assumed this environment be 20 degrees C. And for heat transfer coefficients from the surface of this slab I used 40 watts per square meter Kelvin. I developed this simulation algorithm by using AI tools Copilot and ChatGPT. Here is the summary of this problem definition. The key point is that we now have unsteady two-dimensional heat conduction problem, and our boundary condition is the heat transfer from the surface of this material. Here we see the mathematical model of this kind of case. In this equation, this rho is the density of the material, C is the heat capacity of the material, and K is the heat conductivity. For boundary conditions, the surface of this slab, we typically use this heat transfer coefficient times this temperature difference between the surface and environment. And to get a more stable solution, we typically use, instead of temperature, this temperature difference, local temperature minus the temperature of the environment. When you develop a solution algorithm, it's very important how you handle this time stepping. There are two different methods, so-called explicit and so-called implicit methods. This explicit methods means that your next time step values are based on current time step values. But in implicit methods you take into account also the coming situation. This is more complicated in mathematics, but it generally offers more stable solution. Here is one link from which you can look at what these methods means in mathematics. Here is an example. I developed this Python code in Copilot. This is so-called simple explicit model, and if we look at those results, we see that in the middle of this slab the temperature is almost the original value. It was 90 degrees C. In these corners we see much lower temperature, so this is slowly cooling down. Now this simulation has been running half an hour, 1800 seconds, and I set a control point and I was following the temperature in that location. It was coming down quite nicely. But it seems that when using this kind of explicit method, the time temperature needs to be very, very small Otherwise, this calculation will crash totally. After running my first simulations with explicit code, I developed my Python code so that it's now using this implicit time-stepping method. I was running also some simulations with Ansys Fluent, and I compared the results between this Python code and Ansys simulations, and some modifications were done based on those comparisons. Here you can see some details what was done. Here we have a new Python code. This was developed in a ChatGPT, and this is using this implicit time-stepping method. Here we have the temperature field of the slab. The scale is from environment temperature 20 degrees C up to original slab temperature 90 degrees C. In this picture we see that if we increase the time step, the temperature field will be the same. So this means that when we are using this implicit method, we can use much larger time step, which means much shorter calculation times. This is the main benefit from this implicit method. During the development of codes, a lot of errors were arising. Here are some examples of those errors. So when you are developing this kind of code, you need to test everything and compare results with results calculated with different codes, and if you have some measured data, use that to compare your results. For example, when developing this implicit method, the coding of those boundary conditions must be very well done. There are some recommendations for further development of those codes. Always include this energy balance check average temperatures, and look after those delta D jumps. And if you add more boundary conditions, do everything step by step and check everything. If your slab is not a simple slab, for example, if it is having a fins, I recommend you to use CFD. But remember also that it's always good way to compare results and not to trust too much on CFD. For example, if you have a Python code and you have CFD, then you can compare those results and find out what are the reasons behind those differences. Here are some results from Ansys Fluent simulations. This first case is so-called natural convection case, and here we see the temperature in the middle of the slab, and here we see the slab wall heat transfer coefficient. The scale is from 5 to 12 watts per square meter kelvins. So in this case, when we have only natural convection, this heat transfer coefficient is very small, and I used this pressure inlet boundaries for this environment around that slab, and the pressure outlet boundary about the slab. Here we have the same case, but now we have forced convection. We are pushing air from this end, and we have this pressure outlet boundary at the top. Here we can see that at this end where the cooling air is coming in, the slab is cooling down much more fast. And if we look at the slab wall heat transfer coefficient, it's much higher at this end. The average heat transfer coefficient was 29.6 watts per square meter kelvins in this case. Okay, that was all this time. Thank you for watching and see you. Bye bye.